Hello everyone, let's analyze. So what we have here in front of you is a Texas-sized waffle. Now, the waffle is not actually the size of Texas, meaning the waffle is either bigger than Texas or smaller than Texas. It turns out it's actually smaller than Texas. However, if you were to take the image on your screen and lay it flat on the ground, then if you are in Texas, there is a point in that waffle that corresponds precisely to a point on the ground underneath your screen. Now, if you're not in Texas, go to Texas and start the video from the beginning. In fact, you could say that this Texas waffle is a contraction of Texas. It's Texas shrunk. And if you were to shrink Texas again, using the exact same shrinking rules, then the same point that corresponded to the point on the waffle as to the point that you're standing on would still correspond, so long as you shrunk in exactly the same way. You didn't shift or move or slide or flip or rotate. You just shrunk. And if you kept doing it, well, if you were hungry for a waffle, you'd be disappointed. But also, in fact, the waffle would shrink to the precise point that is underneath your feet that corresponds to the point on the waffle. This is a principle known as the contraction mapping principle, and it's what we're going to talk about today, in addition to talking about the density of polynomials in the space of continuous functions. So let's go ahead and get started. So in the last lecture we talked about metric spaces, which is essentially just a set of elements with a corresponding rule for measuring distances. So consider a function that maps x to y, and x and y have a corresponding metric. Then we say that f is a contraction if there exists some number k greater than or equal to 0 but strictly less than 1, so that for every two elements in x, little x and little y, the distance between f of x and f of y is less than or equal to k times the distance between x and y. Now, since k is strictly less than 1, what we're saying is that however far apart x and y were, they are now closer together after being transformed by f, and this is what's meant by a contraction. So let's take a look at a couple of examples. Let's let f of x be 1/2 x plus 7, where f maps the reals to the reals. And suppose that my metric is just the difference of the absolute value. Well, then f of x minus f of y is half of x minus half of y, which is 1/2 times x minus y. The 7's canceled. So we see that we've exactly satisfied this condition. The difference is less than or equal to a scaling strictly less than 1 but greater than 0 of the absolute value, or that is the distance rather, between x and y. I imagine you likely can conjecture a condition for the slope of this function that would ensure that it's a contraction. Let's try another example. Suppose this time that f maps Rn to Rn, and f of x is a times x plus a, where a is a n by n matrix A is a n-dimensional, or A is a vector in n-dimensional space. And suppose that the supremum over every vector that's a distance 1 from 0 of the distance a times x from 0 is equal to sigma, and sigma is less than 1. Now, of course, what is the metric here? Well, let's assign a metric. And we'll use the Euclidean metric that we mentioned in the last video. The distance of each entry squared, summed up, component by component, and then we take the square root. What's also known as a Euclidean distance. Now, for those of you eagle-eyed observers who have taken linear algebra, you might recognize that as just the difference of the two norm, where we think of x and y as Euclidean vectors, if we want to think about it that way. You may also have recognized this condition, and I'll put this in parentheses, as equivalent to saying that the norm of my matrix, that is an induced norm, is less than 1. An induced norm means I use an existing norm and take the max deformation of the unit circle. In other words, of every vector a distance 1 from the origin, right? That would just be the unit circle or unit ball. How far away does A take it? Right? This would be an induced norm. Well, the distance ax plus a and ay plus a is, and I'm going to go ahead and use this notation. It's the same thing, and again, I think we all know what the 2 norm is. Right, the little a's cancel, and I just have ax minus ay. Of course, here I'm going to use the linearity of matrix transformation, or matrix vector products, to factor that out. Now here I'm going to use some properties of the norm that are not necessarily guaranteed by the properties of the metric. However, this is in fact a legitimate metric, and the 2 norm is in fact a legitimate norm. So you might wonder, can a norm always be used to produce a metric? And can a metric always be used to produce a norm? One of those answers is yes. Now here I'm going to multiply by 1 in the sense that I'm going to divide by the distance between x and y and multiply by the distance between x and y. Of course, you know if x is equal to y, then the distance between ax and ax is of course 0. So we're not really interested in that case. That case kind of automatically satisfies the definition. So here I'm going to use a property of the norm that this is equal to a times x minus y divided by the norm of x minus y times x minus y. Right? I essentially use the fact that If I scale a norm, I can pass the scaling inside. Then I use the linearity of matrix vector multiplication. Now, the difference of x minus y divided by the norm makes this a unit vector, or that is a vector with norm 1, or rather a vector whose distance from 0 is 1. And well, we have a cap on the distance that A can transform a vector from whose distance from 0 is 1. So then this is less than or equal to sigma times the distance from x minus y. Notice that this is just the distance between x and y. And we have satisfied our definition of a contraction because sigma is strictly less than 1, and it is, of course, greater than or equal to 0. And now we come to the contraction mapping principle, which states that if I have a contraction that maps a complete metric space to itself, then it has a unique fixed point. Furthermore, we can say that the unique fixed point is the limit of a sequence of elements where each new element is obtained by applying the contraction to the previous element. In other words, we can almost think of the space being shrunk all the way down to this fixed point as you apply your contraction over and over. Okay, so let's prove the theorem. So what do we know? We know that my metric space is complete. What does that mean? That means Cauchy and convergence are equivalent. If a sequence is Cauchy, it is convergent, and if it is convergent, it is Cauchy. We also know that phi is a contraction. In other words, it satisfies the definition we just discussed. Now, what are our goals, right? We have to prove three things. One, we got to prove that the sequence xn, as defined here, converges. Now, if I define x star as the limit, I need to show that limit is a fixed point. And then I have to show that if I have two fixed points, they are really the same fixed point. Now, hopefully, what we know and what we have to prove are starting to come into focus. For example, if we don't know what the limit is ahead of time, it's hard to prove convergence to that limit. However, we could prove that the sequence shrinks upon itself, which would imply the existence of a limit. And then we could just name that limit x star and prove it's fixed. So let's get started. So let x naught be some element in our space. And as mentioned, we're going to consider this contraction. That is, we're going to consider this recursion. Note that the distance between successive terms in the sequence, since xn plus 1 is phi of xn, and xn is phi of xn minus 1, and by this contraction mapping definition, this is less than or equal to k times the distance between xn and xn minus 1. Similarly, this distance is less than or equal to k times the distance between xn minus 1 and xn minus 2. And this distance is less than or equal to k times the distance between xn minus 2 and xn minus 3. In fact, we can keep on going And what we would get is we would arrive at the fact that the distance between xn plus 1 and xn is less than or equal to k to the nth power times the distance between x1 and x0. So hopefully you can see a few moves ahead. Since k is strictly less than 1 and it's a non-negative number, as I take this to the nth power, this is going to shrink arbitrarily small, meaning the distance between two successive terms, is arbitrarily small. Now, of course, in order to show the Cauchy condition, which is how we're going to get to convergence, which is how we're going to get to testing whether we have a fixed point or not, in order to show Cauchy, we have to show that any two sequence elements past a certain point is arbitrarily small. Of course, we showed any two consecutive elements can be made arbitrarily small. So let's consider the distance between xn plus L and xn, where L is some arbitrary positive integer. Then recall the triangle inequality for metrics. This is less than or equal to the distance from xn to x1, and then from x1 to xn plus L. Right, remember, one way of thinking about the triangle inequality is that detours take longer. If instead of going from xn to xn plus L, I detour to x1, I get something that is longer or equal if x1 is on the way. And similarly, I can use a triangle inequality to break up this term. I'm sorry, this is not x1, but rather xn plus 1, xn plus 1. Essentially, we're going to count from n to n plus L. So I can split this one up to say this is less than or equal to the distance from xn plus 1 to xn plus 2 and xn plus 2 to xn plus 1. If I keep doing that, I get eventually the distance from xn to xn plus 1 plus the distance from xn plus 1 to xn plus 2 all the way through the distance from xn plus L minus 1 to xn plus L. In other words, the distance from xn to xn plus L is less than the distance I would travel if I stopped at every point in between from xn to xn plus L, xn plus 1, xn plus 2, all the way to my destination. And now, because I have consecutive terms, I can use this inequality I derived here. This is less than or equal to what we have the formula here. Here. K to the n times d, the distance between x1 and x0. Using this formula here, I would get k to the n plus 1, the distance from x1 to x0. And if I keep going, I get the distance, k to the n plus L minus 1 times the distance from x1 to x0. Now notice there's a distance from x1 to x0 common to every term, so I can factor that out. There's also a kn common to every term, which I can factor out. And I would be left with 1 plus k squared, so forth and so on, up until k to the L minus 1. which is equal to, right, we've seen a sum like this, a partial sum like this before already. This sum is 1 minus k to the L divided by 1 minus k times this initial distance. So notice L is some fixed integer, k is some fixed number. This initial distance is fixed. The only thing that changes as n increases is this, and well, I can make that arbitrarily small. In fact, this is less than epsilon if, well, actually, if and only if k to the n is less than epsilon times 1 minus k divided by 1 minus k to the L times my initial distance. Actually, scratch that, because k to the L is some number between 0 and 1. 1 minus it is also a number between 0 and 1. So I can simplify this by saying this is less than or equal to k to the n divided by 1 minus k times the initial distance. And this is less than epsilon if and only if k to the n is less than epsilon times 1 minus k divided by that initial distance. That's simpler, and it also makes my choice of n independent of L, because I want L to be arbitrary. Now we can continue. This is much better. Well, k to the n is less than epsilon times 1 minus k divided by the initial distance if and only if the log base k of k to the n is greater than the log base k of epsilon times 1 minus k divided by the distance between x1 and x0. Remember, the log base k asks what number do I need to raise k to equal k to the n? Well, k to the n is equal to k to the n. So this is in fact n. The reason my inequality switched directions is because a log with the base between 0 and 1 is a decreasing function. So then if n is greater than or equal to n, which is, well, any integer bigger than this. Of course, we know there's an integer larger than it because, well, the rows are unbounded, and so are the integers. So then if this is true, we've shown that the distance between xn plus L and xn is less than epsilon. And well, we just let m equal n plus L. Of course, if n is greater than or equal to n, n plus L is also greater than or equal to n. So we've shown our Cauchy condition. Our sequence is Cauchy. So the completeness of x implies that whatever is Cauchy is also convergent. The limit as n goes to infinity of xn equals something, let's name it x star, which is an element of x. So I proved Cauchiness. Because my metric space is complete, my Cauchy sequence indeed is convergent to a point in X. Now, note that phi is continuous. In fact, it's uniformly continuous. Now, how do we know it's uniformly continuous? In fact, our definition of continuity likely calls from comes from real analysis 1, where the only metric we used was the difference of the absolute value. But of course, we can take that definition, swap out absolute value difference with an arbitrary metric, and well, the definition of continuity holds, and so do the conditions, given you're working in a complete metric space. That is, all the implications of uniform continuity hold. Oh, by the way, now how do I know that this is true? Why can I say that phi is uniformly continuous if it wasn't one of my assumptions? Well, I assumed it's a contraction. So let me just put a brief outline of the proof. Let the distance between x and y be less than delta, which I'll define to be epsilon over k. Then the distance between phi of x and phi of y is less than k times the distance between x and y. That's just the contraction criteria. And this distance is less than delta. And delta is epsilon over k. So k times epsilon over k is just epsilon. Okay. So there's a quick proof of why a contraction is necessarily uniformly continuous so long as I'm working in a complete metric space. That means phi of x star equals, by definition of x star, the limit of xn as xn goes to infinity. And because phi is uniformly continuous, I can actually take this limit out. Well, phi of xn is, by definition of how I built the sequence, xn plus 1. And of course, if the limit of xn as n goes to infinity is x star, so is the limit of xn plus 1. In fact, I just get there one step sooner, which, since I get there at infinity, doesn't really mean much. Okay, so now we've proven that x star is a fixed point. Now here's an interesting question. If phi were linear, could x star be anything but 0? Intriguing question. So I've proven 2 out of 3. I've proven that my sequence converges. I've proven that the limit is a fixed point. Now I need to show uniqueness. To show uniqueness, suppose that phi of x star equals x star, right? Perhaps this is the fixed point arrived to by way of taking this recursion. But suppose also that phi of y star equals y star. Well, then the distance from x star to y star is, well, because x star is a fixed point, it's the distance between phi of x star and phi of y star. Which is less than or equal to k times the distance between x star and y star. Of course, if we just think about it for a second, since k is strictly less than 1, the only way this distance can be less than or equal to some number less than 1 times itself is if this distance is 0. Another way of putting it is that if I subtract this to this side, I get 1 minus k times the distance. Sorry, I was being verbose there. Because I subtracted this from here, that's less than or equal to 0. But of course, this distance is greater than or equal to 0. And 1 minus k is strictly greater than 0. Strictly greater than 0, greater than or equal to 0. So then their product is greater than or equal to 0. So because it's sandwiched in between 0 and 0, the distance between them is 0, which is true if and only if x star equals y star. So therefore, we've shown that if I have two fixed points, they were really the same point the whole time, right? Twist ending. We've proven our result. So as a corollary to our last theorem, again, if we have a complete metric space and a mapping from that space to itself, if phi to the k is a contraction rather than just phi, then still phi has a unique fixed point. Now, I'm going to let you prove that for yourself. But just so that we're clear about what I mean when I say phi to the k is just a composition of phi with itself k times. Or in other words, phi to the k of x is phi of x. Of course, k times. So in order to get to the result, you might want to use this fact. That phi to the k applied to phi of x is the same as phi of phi to the k of x. Now, of course, because phi k is a contraction, it has a fixed point. And you're not too far off from showing that phi itself has a fixed point. I'll let you take it from here. I have faith in you. So perhaps one of the most well-known and certainly most visible applications of the contraction mapping theorem is the existence and uniqueness of solutions to first-order initial value problems under certain conditions. Specifically that my rate function is continuous in t and x in some open region of R2, and in particular is Lipschitz continuous in the second component, in the x component, with a Lipschitz constant of k. If this is true, then the initial value problem has a unique solution on some open region centered at t naught, my initial t condition. Now, for the sake of time, I won't prove it, but allow me to give a sketch of the proof. Let phi be a transformation of a function defined by x naught plus the integral from t naught to t of my rate function, f. So phi is a mapping from a function to a function. Now if phi has a fixed point, then x of t would equal x naught plus the integral from t naught to t f of tau phi of tau d tau. Then if x is a fixed point, it's equal to this. If I evaluate at t naught, I get x naught. The integral from t naught to t naught of something that's bounded is 0. And if I take the derivative, then the fundamental theorem of calculus tells me that I get exactly this rate function. Oh, I'm sorry, this should be not phi, but rather x because I have a fixed point. So in fact, a fixed point of this mapping would necessarily solve my equation. Now the question is, does it have a fixed point? Well, as you might imagine by now, if I can show this as a contraction, then it does. And so that's the goal. Let me just sketch the idea of how you might show it's a contraction, and specifically on what set. So let me start with a picture. Suppose that this is t naught and x naught, and imagine is at the center of some circle, and I'll do my best here to center this circle at that point. Okay, and in this circle, because it's a bounded region in R2 and f is Lipschitz continuous, I can say that f is bounded. So suppose for every t and x value in this circle, f is bounded by L, right? The fact that it's continuous and this is a bounded region guarantees a bound for f. Now, suppose now that I take a rectangle inside this circle where this distance from x naught down is L times delta, and this distance from t naught over is delta, and of course the same distance here and the same distance here as here, L delta, where delta is less than 1 over k, and k is my Lipschitz condition. And remember here I'm in the tx plane. This is t and this is x. So then let x be every continuous function from t naught minus delta to t naught plus delta to R, satisfying an initial condition so if x is every function f, that means f of t naught equals x naught. Alright, so the initial condition is satisfied. Oh, I shouldn't call it f because I already have an f. Let's say g. and g of t minus x naught is less than L times delta, where delta is chosen to be less than 1 over k. Of course, that means because g of t minus x naught is less than L delta, g is specifically inside of this rectangle as it passes through here. So this is some potential g of t. Passes through here, and on this region, it's bounded by this region. Right, so for t and t naught minus delta, t naught plus delta. Now I claim that phi is a contraction on x with metric sup over t n t naught minus delta to t naught plus delta f of t minus g of t. Right, to the sup metric that we talked about in the last lecture. So if phi is indeed a contraction on x, then it has a fixed point. And as we showed, that if phi has a fixed point, then that fixed point is a solution to the initial value problem. And because the fixed point is guaranteed to be a function only on this region, that's why we have existence and uniqueness on some region. Now, of course, what would I have to show that it's a contraction? Well, one, I'd have to show that for any function satisfying these three bullets, when passing through the mapping of phi, the outcome also satisfies the three bullets. Then I would have to show that the distance between two functions mapped under phi is less than their distance before mapping. If I can show that, then I can show that phi is a contraction. And if I can show that phi is a contraction, then I've shown that I have a unique solution. So the next theorem we're going to discuss is that every continuous function is just a polynomial. Almost. Let f map the closed interval 0 to 1 to R. Of course, I could change this to a to b, but we'll keep it at 0 to R. Then for any epsilon, there is a polynomial arbitrarily close to f. So while not every continuous function is a polynomial, every continuous function is almost a polynomial, where almost is, well, as almost as you want it to be. So to an applied mathematician, every continuous function might as well be a polynomial. In fact, you can use polynomials to approximate functions, and that's actually at the core of many applied mathematics techniques. In fact, the Bernstein, which is it again? Oh yeah, Bernstein polynomial defined by Pn of x from k equals 0 to n, and choose k, f of k divided by n. Since I'm dealing with the interval 0 to 1, this is essentially a even partitioning. X to the k times 1 minus x to the n minus k. So this Bernstein polynomial, which of course uses f as part of its input, converges to f uniformly which is how we get this result. So let's prove the result. So let's begin with the binomial theorem. X plus y to the nth power is equal to the sum from k equals 0 to n, and choose k, x to the k, y to the n minus k. We'll call this, for now, equation 1. All right, we're going to use the binomial theorem as building blocks of this Bernstein polynomial to eventually prove uniform convergence. Now, if I differentiate 1 with respect to x, then multiply by x, I would get n times x plus y to the n minus 1. Then I'm going to multiply by x. So I would get this on the left. On the right, I would get this summation. And choose k times x to the k times y to the n minus k. Right, I brought down the k, but I don't have k minus 1 because I also multiplied by x. Well, that was so much fun. Let's do it again. Let's differentiate 1 twice with respect to x, and then multiply by x squared. That is, we're going to differentiate this twice and multiply by x squared. That'll give us n times n minus 1 times x squared times x plus y to the n minus 2 on the left, and on the right we would get the sum from k equals 0 to n, and choose k times k minus 1 times x to the k times y to the n minus k. So let's call this equation 2, and let's call that equation 3. Now let us define this function rk of x to equal, and choose k, x to the k times 1 minus x to the n minus k. Now, let's look back at equation 1. Let's insert y equals 1 minus x into the expression 1. Then x plus 1 minus x raised to the nth power, well, of course, that equals 1. But it also gives us a very elaborate formula for the number 1. And choose k x to the k, 1 minus x to the n minus k. And well, notice that all of that is just rk of x. So if I define rk in this way and sum up these rk's from 0 to n, I get 1. Similarly, from 2, I get n times x. Again, I'm inserting y equals 1 minus x, which means this 1, and I'm left with just nx equals k times rk of x. And from 3, n times n minus 1 times x squared equals the sum k times k minus 1 times rk of x. Again, from 0 to n. So I've taken the liberty of rewriting the three identities we just derived. Given the way we defined rk, if I sum them all, I get 1. If I sum k times rk, I get n times x. And if I sum k times k minus 1 times rk, I get n times n minus 1 times x squared. Now I also pointed out that I could split up this sum into k squared rk minus krk this way. And of course I already know that the sum of krk is nx. So we have these three identities. Let's continue forward. So we can use these three identities to form a new one. If I sum from k equals 0 to n, k minus nx squared rk of x, well, that equals k squared rk minus 2nx krk plus n squared x squared sum of rk. Of course, all of these from k equals 0 to n. K equals 0 to n. And in fact, I know that this minus nx is equal to this. This term here is nx, and this term here is just 1. So if I carry out just a bit of arithmetic, I obtain this result. Now, since my function that I'm trying to approximate by a polynomial is continuous on the closed and bounded interval 0 to 1, it is also uniformly continuous. Right? Since any continuous function on a compact set is automatically uniformly continuous on that compact set. Furthermore, it's also bounded. So this also applies that there exists some max value m for which f of x is less than or equal to m for all x on that interval 0 to 1. And now is where the for any epsilon there exists an n comes out. For epsilon greater than 0, there exists a delta greater than 0 such that for every xy satisfying x minus y is less than delta, well then f of x minus f of y is less than epsilon, right? For any epsilon, I can find a delta that guarantees this result because of uniform continuity. Notice that my delta depends only on epsilon, not on xy, right? It works for every xy within a delta radius of each other. F of x minus Pn of x equals f of x minus the sum from k equals 0 to n f of k divided by n times rk of x. This is the Bernstein polynomial using our definition of rk. Well, that equals the difference between f of x and f minus k over n times rk of x from k equals 0 to n. Now why can I put f inside of here? Well, imagine if I separated this, I'd have the sum of f times rk. Because this f is not indexed, I can factor it out, and the sum of rk is 1, as we've already established. Now let's take a look at this difference. Remember, for a given n, as k goes from 0 to n, I have essentially just an even partitioning of the interval 0 to 1. And well, if x is close enough to this partition bound, then I can make that difference small by the uniform continuity condition. Now, of course, when x is not near k over n, in other words, that integer, we have to make sure that that is small as well. So let's let k1 essentially be every indice within delta of x. All indices k such that the partition k over n minus x is less than delta. Then of course this k1 will of course depend on x. And let's let k2 be the other indices. Right, so the remaining indices. So then my difference which is equal to this can be split into the indices where I'm within a delta range, and of course this set's going to depend on x. As x moves, the indices close to x will of course move with it. F of x minus f of k over n times rk of x plus, well, all the remaining indices. F of x minus f k over n times rk of x. Now using a beefed up triangle inequality, I get f of x minus f of k over n times rk, and I'll put this in absolute values. Plus the remaining sum, f of x minus f of k over n, an absolute value times rk, k and k2. Now remember, these indices guarantee that the index, or that partition interval, is within delta of x. And so long as this argument is within delta of x, this difference is less than epsilon. And of course, this term here is less than or equal to 1, because if I add up all the RKs, I get 1. Well, I'm taking a subset of them, so I get less than or equal to 1. Now notice I can apply the triangle inequality to this further by saying this is less than or equal to f of x plus f of k over n. And remember that f is bounded. So this is less than m, and this is less than m. So I get plus 2m times the sum rk, k in k2. So we know already that this term is less than epsilon, but what about this term? Well, here is where a little bit of the previous work and setup becomes fruitful. K is in these other indices if x minus that partitioning, or that partition interval delimiter, is not less than delta. In other words, is greater than or equal to delta. If I divide both sides by delta, I get x divided by delta minus k over n delta is greater than or equal to 1. Now let me put this over a common denominator. I get xn minus k divided by n delta is greater than or equal to 1, and it's still true if I square both sides. Of course, that's 1, and this would equal xn minus k squared divided by n squared delta squared. Because I'm squaring a number, I don't have to worry about the absolute value anymore. So because this number is bigger than 1, I can deduce a new upper bound for this. Two m times the sum of k and k2 rk is less than or equal to 2m divided by n squared delta squared and x minus k squared times rk of x from k equals 0, or rather for k in k2. And if I had all the indices, we know exactly what that sums to because we did it on the previous page. So this is less than or equal to 2m over n squared delta squared times nx times 1 minus x. Now, of course, because x is bounded between 0 and 1, this is also bounded. So I get 2m divided by n delta x times 1 minus x. Which, of course, because m is a bound on f, it's fixed. 2 is, well, it's 2, it's fixed. Delta is also fixed. And x is some particular number, and this goes to 0 as n goes to infinity. Now, we should say that I can make this arbitrarily small regardless of x. Well, I can, because in fact, this is a bounded function of x. In fact, it's, if you were to compute it, it's less than a quarter. Meaning if I wanted to tie up a formal bow on this proof, if n is greater than big N, which is chosen to be greater than m divided by 2 delta squared epsilon, then the difference between my Bernstein polynomial and f is less than, well, in fact, I would actually get 2 epsilons. Which means my Bernstein polynomial is as close to f as I like, so long as I choose the order of the polynomial large enough. So let me just mention this generalization of the Weierstrass theorem, which is the Stone-Weierstrass approximation theorem. It essentially generalizes to any set of continuous functions that form an algebra and satisfy these other two components. So let XD be a metric space, let A be a subset, and suppose B is the set of continuous functions that map my subset A to R. Remember, A being inside my metric space. Well, then if this set of continuous function B is an algebra, in other words, sums of elements remain in B, products of elements remain in B, scalings of elements remain in B, f equals 1 is an element of B, and for every unequal pair in the domain A, there's a function f for which f of x is not equal to f of y. Then we say B is dense in the set of all continuous functions mapping A to R. Now, what do I mean by dense? I mean that the closure of B, right, that is B joined to every accumulation point of B, equals the set of all continuous functions from A to R. Now, just as a quick note, the set of all polynomials in fact satisfies the conditions here. So we see that this is just a generalization of what we've proven previously. And the fact that any function is arbitrarily close to a polynomial makes functions accumulation points, that is, continuous functions are accumulation points of polynomials. So if I were to take the closure, in other words, if I were to add or take the union of all polynomials and everything arbitrarily close to all polynomials, that would be the closure, and I would get, in fact, all continuous functions. So we can say that the set of polynomials are dense in the set of continuous functions on a closed interval. And that's all for today.